Hello everyone. In this video, I'll show you how you can remove multicollinearity from your dataset using Principal Component Analysis or PCA. So let's get started by importing the necessary modules. I have a file called as training_data.csv which I load into my data frame df. Let's visualize the first 5 rows of my data frame. As you can clearly see, the data frame contains 4 columns x1, x2, x3 and y, where x1, x2, x3 are my features and y is my target variable. One more observation is all the values are continuous in nature and none of the values are discrete or categorical in nature. Let's also print out the total number of rows and columns in my data frame. As you can clearly see, the total number of rows in my data frame are 155 and the total number of columns are 4. Now that we've gone through the basic idea of what the data frame is, let's go on to separate the data frame into x and y, where x consists of features and y contains my target variable. Since this video is all about removing multicollinearity from a given dataset using PCA, firstly let's find out if my dataset actually has multicollinearity by plotting a heat map. So this is how my heat map appears. If I start with the first column, which tells me the relationship of every feature with my target column, I can clearly see that all my features are heavily correlated with my target column. X1 has a correlation coefficient of 0.91 when compared to the target variable, and X2 has a correlation coefficient of 0.81 when compared to my target variable. So this is how my overall target variable distribution looks in terms of correlation coefficients. Let's come to the next part, which is actually finding out multicollinearity in my dataset. One of the assumptions of linear regression is that there should be little to no multicollinearity in order to have a good, robust statistical model. But if you observe this part of the heat map, for feature x1, it has a correlation coefficient of 0.95 when compared to x2. So as x1 increases, x2 would be also linearly increasing. When I compare x1 with x3, this is the correlation coefficient that I have, which is 0.99. Similarly, x3 when compared with x2 has a value of around 0.97. So this entire 3 cross 3 matrix is a good enough idea to give me that there is heavy multicollinearity in my dataset. All three features are heavily correlated with each other as well as related with the target variable. So if I create a linear regression model out of it, I won't be getting the best model out of it because I am violating the multicollinearity assumption. But still, let's go forward and create a linear regression model using the StatsOLS package. Since I want a linear regression model with the intercept term as well, I first add a constant column to my existing features that are there. So I'll have x1, x2, x3 feature. I'll also have one more column which would be appended to my data frame, which will just have values of 1. I then pass in the values of my newly created featured data frame and my target variable y into the function sm.ols. Now that I have passed in the values of y and x, that is my target and features, let's go on to fit the model. After fitting the model, let's also visualize the summary table that is generated from the OLS report. As you can clearly see, I don't have to go anywhere here, although it looks to be a very good model having a very decent enough R squared and adjusted R squared values. The only thing that I am worried about is the condition number is large, which is this value. This simply indicates that there is strong multicollinearity that exists in your overall model that you've created. Thus, the standard errors that you've computed cannot be relied upon when you use this model for prediction. So how do we tackle multicollinearity? There are other techniques such as variance inflation factor or VIF score that can help you find out if your features are heavily correlated to each other or not. But the idea of this video is to use principal component analysis to reduce multicollinearity in your overall dataset. In order to do that, first let's split out our three columns, that is x1, x2 and x3 into three corresponding variables, that is x underscore line, y underscore line and z underscore line. So I run the cell. Since I've mentioned that there is heavy multicollinearity between the three features, let's visualize the three features in three-dimensional plane. So this is the scatter plot of my features x1, x2 and x3 in a three-dimensional plane. So as you can clearly see, there is an increasing trend line that you can observe in the scatter plot. So as x increases, y increases and z increases, all the values seem to be increasing in a perfectly correlated manner. If I have 2 points in 2 dimensions, both of them can be connected via a line. When I have a three-dimensional plane consisting of three features in our case, then if I have to join points, then I'll consider a plane. So the next thing that I do is I create a function called as plot underscore plane underscore with underscore points that accepts the values of x, y, z, plots a scatter plot that are provided to the function, along with creating a plane out of all the three sections that you have, that is x, y and z. It will create a plane that could fit in all the data points that you've provided. The plane creation is something similar to creating a linear regression line, wherein here the features would be a two-dimensional feature space which would be x and y, and my target would be the z plane. Now if this idea is clear as to what we've implemented in the above function, let's call the function with the given inputs x, y and z that we've separated out, and this is what we observe. As you can see, all the points in my scatter plot lie on the plane. That is what is denoted by the black dots if you can see in the graph. So whatever plane that I've built is really well fitted to the entire points that I have. Nothing is out of my plane. If any point would have been out of my plane, that would have been denoted by a different color. Since all the points are denoted by the black color, I can safely assume all the points lie on the plane. So there is a clear case of multicollinearity where my features x1 and x2 can easily explain why. That is why my plane is so well fit to all my points that are scattered in the 3D plane. Now that we have understood that there is multicollinearity in the data, let's try to remove it using PCA. Before we even apply PCA, the first thing that we have to do is standardize the inputs. For standardizing, I'm using sklearn's pre-processing function called as standard scalar, which would standardize features by removing the mean value from every value of that column and dividing it by the variance that exists for that column. So I run the cell. Now that I've standardized my inputs, the next thing that I do is I call the PCA function. I fit my feature values, that is my x underscore standard array. I plot the overall variances explained by each component when I apply PCA. The only difference is rather than plotting individual contributions, I plot an overall cumulative sum of the contributions so that the sum total of all the contributions turns out to be 1 or 100%. As you can clearly see, the first principal component itself gives me a value greater than 0.9975 and the other two values are very small and they add up to a total of 1. Let's see the actual outputs in numbers rather than visualization. As you can clearly see, the total variance of the data captured by the first principal component is around 98.1%. The total variance captured by the first two principal components amount to a total of around 99.8%. So most of the variances are captured by the first two components itself, and the third component just adds it up to 100%. Let's see their individual contributions as well. So I run the cell, and as you can clearly see, the first principal component constitutes around 98% of the overall variance that is captured by this component. The second principal component captures around 1.6% of the total variance, and the third component is capturing a variance of less than 1%. So this is how my total overall variances are captured for the given set of data that I have. Since 98% of the total variance is captured by the first principal component itself, I call the PCA function again, and now I use something called a split underscore transform, which takes in the standardized inputs, which is x underscore std, and I fit it with just one principal component. Since I'm using OLS and I'm also interested in the intercept term, I call the add underscore constant function and I fit my OLS model with that constant function. And now, as you can clearly see, the model is really well fit, where there is no warning given out stating that there is heavy multicollinearity or something of that sort. So I've reached at a point wherein out of 3 features, I have come down to a point wherein I've used one feature that explains the overall variance in the data set that had 3 features. So this is the magic of PCA. There is absolutely no multicollinearity now, considering there is just one feature that I have. If I plot a scatter plot between my standardized inputs for PCA and the best fit line along with it, this is what I observe. So overall, it's a very good fitting line for the given data that I had. So this is how you can smartly remove multicollinearity using PCA. The concept of using PCA for removing multicollinearity is really good, but this method cannot be used in cases where model interpretability is of prime importance. If the business wants to understand which feature is relevant, which feature is not relevant, in such a case, you cannot use PCA for removing multicollinearity. In cases where you're just chasing a good model, irrespective of what the features are or what the end features are, what do the end features imply, then using PCA for removing multicollinearity is a good option. So again, I repeat, this function works really well when you don't want to interpret the results that you derive from the linear regression model, or there is nothing that you want to explain to the overall business that, hey, listen, this feature is having a weight value of XYZ or something of that sort. So this was my take on how you can use PCA for removing multicollinearity in your dataset. I hope you found this video informative. If you do have any questions with what we covered in this video, then feel free to ask in the comment section below and I'll do my best to answer those. If you enjoy these tutorials and would like to support them, then the easiest way is to simply like the video and give it a thumbs up. And also it's a huge help to share these videos with anyone whom you think would find them useful. Please consider clicking the subscribe button to be notified for future videos. And thank you all for watching the video.